So looking up at the top, this is just examples of different situations where something depends on something else, which in a nutshell is this whole course, this whole year. Okay, we're just going to be dealing with functions. We'll deal with a few relations in the next two paragraphs that kind of differentiates the two. But the majority of this is you've got an independent and a dependent variable. One is always going to affect the other. Going to this second paragraph right here. When the value of one variable is related to the value of a second variable, it is called a relation. Okay, however, whether you're underlining, highlighting, I would point that out. That graph can look like anything. You could draw a picture of a dog on a graph, and technically it's a relation. Okay, any picture or any dots or whatever on a graph is a relation. If x and y are two elements in a set, and if a relation exists between x and y, then we say x corresponds with y, or that y depends on x. Okay, and that's just saying, again, you've got something that's dependent on something else. That's all that's saying. This next sentence or two, this is probably, I would say, the most important part of all these definitions. You need to know what a function is. Function is a relation where y depends on x. Okay, so a function is a special kind of relation for when each input, or x value, there is only one output, or y value. Okay, so it's a certain kind of relation, and we'll talk about how you can define whether it's a function or not a function here in a minute. Hopefully that's all review. All right, whenever you're measuring a graph, you use domain and range. The set of x values is your domain. The set of y values is your range. Pretty much every graph that we do this whole school year, you're going to be asked to identify the domain and range. If you have struggled with that in the past, you need to come see me. Okay, we'll have a couple examples today, but that's really it. So make sure that you're clear on all of that right there. For a function, y equals f of x, the x variable is the independent variable because it can be assigned any number from the domain. The y variable is the dependent variable because its value depends on the x. Okay, so as the x changes, then the y changes. The independent variable also is called an argument of the function. That's not a huge deal. You won't see that a lot. Okay, but you will. It's just good to know. Alright, these next few sentences. Follow me here. Thinking of the x variable as an argument can make it easier to find the value of a function. All that's saying is you're going to take the value of an x variable, whatever x value you want to pick, and you can put it into the equation to figure out what the output is with the y value. For example, if f is the function defined by f of x, that's how you would say that, equals 3x plus 7, the f tells you to multiply the argument by 3 and add 7. Therefore, f of 6 is 3 times 6 plus 7. To put that into layman's terms, okay, let's right underneath where it says f of x. Let's say you're given that, and then you're given, okay, what's f of 2? All that's telling you to do is substitute 2 in for x. Okay, so I would do 3 instead of x. I'm going to put 2 there. And then plus 7. 3 times 2 is 6. 6 plus 7 is 13. So you would tell me that f of 2 is 13. The x is 2, the y is 13. That's what that's saying. Going down to these right here, these are different representations of functions. You got a table, you got mapping, ordered pairs, and graphs. We will deal with, the one that we won't deal with a lot is the mapping diagram, but tables, ordered pairs, and graphs we will be dealing with a lot. Now, as you can see, let's start with the table here. Every x value only has one y value. So this would be considered a function. What would make this not a function is if there was another point down here and you had a repeating x value with a different y value. That would make it not a function. Whenever you have a mapping diagram, as long as each x value only has one arrow coming from it, it is a function. If we had this, let's say we had 24, but imagine that's inside that oval, and another arrow coming from 3, that situation right there means that it is not a function. The ordered pairs is probably, in my mind, it's probably the easiest to identify whether or not it's a function. And that's all you got to look for. This is a function because no x values repeat. If you have a repeating x value, then it's not a function. Does anybody remember looking at a graph, what you do to tell whether or not it's a function? So if I'm looking at a graph, what can I do to determine if it's a function or not? Or can anybody read the words that's below the word graphs? We'll pass the vertical line test. There you go. If you don't remember vertical line test, you just draw vertical lines. If it crosses through the graph more than once, any one vertical line, it's not a function. Okay, and if on that kind of graph you would put the vertical lines through the dots. If you have a vertical line that goes through 2, then it would not be a function. Down here you've got a parabola. It is a function. None of those vertical lines crosses through it twice. Okay. So those are the different representations that we'll see throughout the year of the different functions we'll talk about. Going to the paragraphs below. This is talking about really the kind of data that's on there, or the kind of function that you're dealing with. It says when the domain of a function has an infinite number of elements, it can be graphed with a linear or smooth curve, and it is called a continuous function. Okay? Continuous function, essentially, it's a line. If you look at a graph and it's not a bunch of points, it's a line, you're looking at something that is considered continuous. 98% of the stuff that we do in here this year is going to be continuous. Then you've got discrete. This is just a bunch of points, singular points. Okay, so those two graphs up here, that one would be discrete. This one would be an example of a continuous. It's an actual line, or it's just a bunch of points. Alright, a function is a one-to-one function if for each x value there is only one y value, and each y value there is only one x value. So this is kind of weird, and you'll see it come into play towards the end of the notes today. But if you look up there at the mapping, Okay? So let's say, so this would not be a 1-to-1 because this 5 has 2 x values attached to it. Alright, let's say that this arrow is not there, coming from the 1. And there's a 2 up here. That would be a 1-to-1. Nope, essentially no repeating x values, no repeating y values at all. You'll see how we can use that knowledge whenever we talk about the horizontal line test. Or sorry, not horizontal line test. Whenever we talk about inverses, which is at the end of the notes today. Okay, but being able to recognize that can help you out with whenever we get to that inverse stuff. The even function, the odd function, we'll get to those eventually. I'm not too concerned about those right now. So go ahead and go to the next page. So on this page, what I want you to do is, and you're going to kind of work through this whole page, not by yourself. Any kind of practice or example problems in here, there is no individual work in here. Okay? It's all working together as a group, help each other out. I will tell you the instructions on 1 is a little confusing probably. Where it asks you for the domain and range, I want you to tell me what the domain and range are actually measuring. So you're not going to have numbers there. You're telling me what is the domain measuring, what is the range measuring. Okay, so let's just look at these first few, and then I'll let you go on and continue to work. So let's look up here. Follow along with me. So this first one, is this relation, I've got x's and I've got y's, is that a function? Yes or no? Yes. Why? Okay, the x's don't repeat. And now it's kind of tough because whenever I would look at this just because there's arrows, I would look at this like I would look at a mapping. And there's kind of different strategies depending on how it's being represented to you on how to determine whether or not it's a function. If it's not a function, then I would have 2 arrows coming from the same x value. Okay? What is the domain representing on this problem? Gas stations. And the y value? Price per gallon. On the second example, is this a function? No. Why? Because I've got that 0.71 that has 2 arrows coming from it. What's the domain measuring on this one? Carats. And then the y value is measuring the price. Would either one of these be considered a, sorry, it would help if the screen wasn't frozen. There you go. Would either one of these functions be considered a 1-to-1 function? No. Right? On mapping is probably the easiest way to determine that because you just got a bunch of straight arrows. Looking at number 2, on this first example, is this a function? Yes or no? Yes. Why? There's no repeating x's. Okay? On the second example there, is that a function? No. Why? Okay. You've got -3 repeating. Any questions on how to determine, okay, what is a function, what is not a function? At least in those situations. Alright, so go down here, work on, if you haven't already, start to work on these graphs. You've got a little bit of a word problem. And then you've got that function notation down here. Okay, where I was kind of talking about it's just substitution. Don't overcomplicate it. So looking at at number 3, the first graph, would that be considered concrete or discrete? Or sorry, continuous or discrete? Discrete. Okay, it's just a bunch of points. So this one would be discrete. Before we do domain and range, would this be considered a function? No, why not? Because right there at -1, if I drew a line right there, it goes through it twice. Domain and range on discrete, it's a little weird, probably just because we don't do it a whole lot. But it should be kind of easy. Okay, you've got kind of those weird little parentheses. And then you're just going to list the numbers. So the x values that I have is -1 and 4. The y values that I have is -2, 1, and 4. This is another way that you can tell whether it's a function or not in the case of a discrete data. If you have more y values than you have x values, then it's not going to be a function. Because somehow those two x values have to account for all 3 of those y values. That means one of them's repeating. Going to number 4, is that one continuous or discrete? Continuous. Jeremiah, would that be a function or not? Why not? Because vertical line test. Okay. Can somebody tell me what the domain would be? -5 to what? To 3. I'll kind of talk about domain here in just a second as far as what you need to look at. So a lot of you are probably used to writing it like this. And on the next page, we're going to talk about 3 different ways to write the domain and range. The one way, this is called inequality notation. The one way you're going to see me write it the majority of the time would be this right here. It's called interval notation. I do not care which way you write it. I'm able to read all 3 ways. I know that both of those are the same thing. So you write it the way you want to write it. You do need to be able to read it both ways. Because if it's a multiple choice test or quiz, whatever, and those multiple choices are domain and range, one may be an inequality, one may be an interval. So what would the range on this be? -1 to 3. If you have forgotten domain and range, domain, better yet, do any of you remember this acronym right here? Diller is probably taught to you by your Algebra 1 teacher, Diller-Robot. Raise your hand if you've ever heard that before in your life. Okay. So, what does Diller stand for? What does the D stand for? Domain. What does the L and the R stand for? Left to right. And it's talking about the input. Robot. Obviously, the R is going to stand for what? Range. The B and the T? Bottom to top. And it's going to be the list of your outputs. Now, whenever you're doing domain and range, just to give you kind of a comparison Something to think about, because I have some people that struggle with this. And I'm going to end up having a lot of football analogies, because that's what I coach football a lot. But if there's a play that starts on the negative 32-yard line and it goes to the positive 48-yard line, if you fall, let's say it's a run play, and the running back, he takes the ball and he just has this crazy path to get there. All of the up and down does not matter. If you're doing the domain, all that matters is where he starts. So it would be from the negative 2 to the positive 48, where he starts and where he ends on this oval. Left to right, where it starts and where it ends, left to right. Range, same thing, you're just thinking bottom to top. I've had a lot of students in the past, they'll do that right there on the graph. They'll write a box around it. They'll draw a box around whatever shape that is, and that kind of helps. They know they're going from the edge of the boxes. Going down to number 5. You got some girl that delivers for a restaurant. She's paid $18 per day, 4 for every order. So on this, which one of these equations represents this situation? The first one or the second one? Raise your hand if you think it's the first one. Raise your hand if you think it's the second one. What do you think, Jack? Jake? Is it Jack or Jake? Okay. What about you, Jacob? First one or second one?
First one or second one? I would say second one.
Second one? Okay. Alright, so if you put down the first one, if you put down the second one, you're correct. Okay? She gets paid that $18 a day. Nothing is going to change that 18. If she shows up and she makes 0 deliveries, so I would put 0 in there for X. 4 times 0 is 0. 0 plus 18 is 18. She got paid $18 that day. She goes in, she makes 2 deliveries. 4 times 2 is 8. 8 plus 18 is 26. She made $26 that day. Alright? So, make sure you have that second equation written down. Alright, and I'm going to do my best to explain to you the why behind a lot of these things. And it's not necessarily specific to just this, a linear equation, but this kind of problem. And obviously this is a very simple application problem. But if you ever plan on making money or getting paid, money's actually, you may not know this, it's counted by numbers. There's numbers on dollar bills and stuff, so that's how you count money, is with numbers. And if you want to make sure that you're getting paid what you're supposed to be getting paid, then that's having number sense. It's being able to calculate how much you're being made. Or you can just trust the company that's paying you. Which a lot of companies, if they can save a little money, no matter how, they're going to. That's the world. All right, this last year, this school year, teachers in Frisco ISD, there's kind of, and it was kind of a unique situation. There were 3 different raises that we got, and they were calculated differently. You would be surprised how many teachers had no clue and could not calculate what kind of raise they were going to get. Except for the one raise that said, you're getting this amount on this paycheck. But the other ones had to deal with percentages and their base pay and how many years they've taught. And so they don't know if they're getting paid the right amount. And the explanations that a lot of teachers had, it was comical because they had no clue what to even look at. Okay, so and there's a lot of problems you're going to see in here. that's easy to apply it to life because it's dealing with money. All right, if you plan on just not working and not making money, then I don't know what to tell you. I guess it doesn't apply. But there's a lot of this, and this is a pretty, like I said, this is a pretty simple example of it. They can easily get much more complicated whenever you're talking about percentages, interests, things like that. Going to number 6. For the function f, defined by f of x equals x squared minus 1, evaluate the following. So kind of what I was saying at the beginning. All you're doing is if it's f of 3, you're plugging 3 in for x. Okay. 3 squared is what? 9. 9 minus 1 is? 8. So f of 3 equals 8. On letter B, raise your hand if you got negative 5. Raise your hand if you got 3. Okay. You've got to be careful. You've got to put the parentheses in there. Okay. If you got negative 5, do me a favor. Grab your calculator and put it in there exactly the way it is minus 1. Put it in there exactly the way I have it and see what you get. Because if you don't do parentheses, and it's not necessarily a calculator error, I wouldn't say it's necessarily a user error, it's kind of a miscommunication. You're telling the calculator to do something that it's not actually doing. It's doing something else. Okay, so whenever you put that in, you should get 3. The problem occurs here. And so if you put this, let me change that so we can see it better. If you put this, that's how you would get negative 5. Okay? Because all that's doing is that's squaring the 2. It's not doing anything to the negative except just leaving it there. So 2 squared is 4, and then it's just going to put the negative on there. Okay, but you have got to be careful when putting that into your calculator. So on this, f of negative 2 is going to give me 3. Going to this last one. Do not complicate this right here, please. If you're squaring a fraction, square the numerator and then square the denominator. 3 squared is 9. 2 squared is 2 squared? 4. So 3 over 2 squared becomes 9 over 4. Minus, you got a fraction, so you need a common denominator. What over 4 is the same as 1? 4 over 4. 9 minus 4 is 5. Keep your common denominator. You got that, Jacob?
Sure.
Pick your head up, please. Alright, I'm going to go through this as quick as I can. These are the 3 different notations. Not really going to talk a whole lot about the paragraphs up top. It just kind of explains, hey, there's 3 different notations that you can write domain and range in. As far as explaining to you the why things, I wish I had an explanation for this. I don't know why there's 3 different ways to write the same freaking thing, but there is. So, first we're going to draw the connections to the 2 forms that you're mostly going to see in here. Inequality and interval. Okay, and I'll talk about set notation in a second, but you're not going to see that a lot. So on this first one, all real numbers from A to B, including A to B. So if you're writing it in inequality, you've got to have the equal signs there. Converting this to interval notation means that you have brackets. Equal to is brackets. Without the equal to is parentheses. So that's how you can go from one form to the other. These are the 2 situations where a lot of people struggle with whenever you're dealing with infinity. All numbers greater than b. So that's what that means. X is greater than b. So in my mind, I say it a little bit differently depending on how it's written. If it's all numbers greater than b, that means over here I'm going to go from b and it's going to go all the way up to infinity. So that's how I'm going to write that. here is all numbers less than or equal to a. So if it's a and it keeps going down forever, I'm going to start at negative infinity, and then it goes up to a. Now, because it's equal to, this should be a bracket. So change that parentheses right there to a bracket. It's a typo on this. Not going to talk a whole lot about this last one. We will see it eventually here and there, but we will not see it a lot. This is what it's going to look like if there's a gap in the graph, whatever that may be. Okay, you got, I don't know, you got this, and then there's some gap in the graph where it's not connected, and then you got that. This is what's called a union sign. That's all that represents, is the gap that's in that graph. Okay, you don't have to overcomplicate that too much, but you're just converting this to this. So again, I missed that typo yesterday. That's my A day. Because these are equal to's, these should be brackets, not parentheses. So if you'll make that small, I'll give you a second or two to make that small adjustment. Alright, those are the main ones. I want you writing, or want you understanding and being able to read. Looking at your set notation, all the set notation is inequality, except at the very beginning. If it's domain, you have that X and that slash, that line. But if you look, this was just copied and pasted right over to this spot. Okay, so it's the same thing as inequality notation. So I want you to go to that table below. And I'm going to save us a little bit of time on this. These boxes right here, you're just going to write one set notation. These boxes, you don't have to write. Okay, but I do want you to write all the inequalities. I do want you to write all of the interval. Be careful on 3, 2, and 4. Okay, any of them that involve infinity, be very careful whenever you're writing that. All right, so there's the last one up there. Any questions on this? Emphasis on brackets, parentheses. Okay, because guys, there's come test time. You're asked to write domain and range. That may be an option. 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 So the numbers are all the same, but you got to know what the parentheses and the brackets represent. All right. Now, one quick thing, one easy way to cancel out the answers that don't make sense. If you can never be equal to infinity, okay, you should never have a bracket on negative or positive infinity. That should always be a parentheses. So those would definitely be wrong. All right, awesome. So last idea of kind of today's notes, and I know today's notes are long. It's a lot of review. It's a lot of stuff that you probably heard in Algebra 1. This is the one thing that you probably did not talk about in Algebra 1. So if you've kind of been in and out a little bit, please kind of zone back in here. An inverse relation reverses the pairings of a relation. So that is exactly what we're going to do here in a minute. Okay, we're going to take, it's pretty easy whenever you're looking at a table or a mapping. That's exactly what we're going to do. Our x's become y's, or y's become x's. So whenever we get to that point, you'll see how easy it is. Alright, now this next part. The inverse of a function may or may not be a function. If the inverse of a function f of x also is a function, then it is called the inverse function and is written f of negative 1 of x. Okay, so that just means, hey, this is the inverse of f of x. That's all that means. The inverse of a one-to-one function, there's that again, will be a function. If the inverse of a function is not a function, then it is called an inverse relation. Okay, was that as painful to listen to as it was to read? Yes or no? It wasn't painful to listen to? Y'all are smarter than me, because that sounds awful to me. I said the word function and relation and inverse at least, I think, 74 times there. Okay? So put this into layman's terms. You'll have an original function, whatever it may be. Okay, the first one we're going to look at is 2x plus 4. Okay, it's any kind of function I give you. Every function has an inverse. Okay, so you have an original. We can do something to it, do certain stuff to it, and we can see that original function's inverse. Just because the original is a function does not mean that the inverse is a function. And that one-to-one thing is going to kind of come into play there. Okay? So, let's look at this first example. So, the function we're dealing with is 2x plus 4. Complete the mapping diagram for the inverse of the function. So, if you have a table or a mapping diagram, you have what is representing the original. To do the inverse, it is not very difficult. What were your y's are now your x's. What were your x's are now your y's. It's that simple. So, is this the original function right here? We can go ahead and put this next to it so you can kind of start associating that notation with inverse. This notation with just the original function that's given. Is the original function a one-to-one function? Yes. No repeating x's, no repeating y. It's a one-to-one. If the original is a one-to-one, the inverse is going to be a function. Now there's not a y here, but I want you to have that written down though. So you can put yes, because the original, just so you know where we got this answer, the original is a one-to-one. So next, I want you to take the points from the original and then the points from the inverse. So your points are just here, -1, 2, 0, 4, and so on. You're going to graph those on this right here. I'm going to make it all nice and color-coded for you. So my original, I've got -1, 2. I've got 0, 4. 1, 6. And I've also got 2, 8. My inverse I'll put up here in blue. I've got 2, -1. I've got 4, 0. I've got 6, 1. And I've got 8, 2. After that, can anybody tell the relationship between those two, or what do you notice about those two functions in relation to the dotted line that's on the graph? Somebody tell me.
I don't remember how was it called, but it went from 2 to a half, like it changed. I don't know how was it called.
Okay. I think you're referring to the slope.
Yes. No,
Okay.
no, yeah, the slope, but then like the change from like the 2, 1, yeah, from the 1 to. That's what
Okay. Okay. Maybe this will help. Look up here. You don't have to, but I'm gonna go ahead and draw these lines here. So what do you notice about those two lines in relation to that y equals x line? Okay, they're crossing it, but what else? Do what? No, not negative. I mean, yeah, they kind of are. I mean, they go down a little, down there, but what else? Avery? Okay. They do meet at a point. What are they doing about that line? Daniel, right? Take a crack at it, Daniel. We determined that they cross. We determined that whatever else we've said. Look, I'm looking for a certain word. Not intersect. What was that? Okay, they're on opposite sides, but exactly how? Not parallel, but now we're on the right track. Not perpendicular. God, guys, get out of geometry. It's an awful place. They are. Do what? No. Flipped or reflected. It reflects. It's reflecting across this line. Okay? If I take. So what do you notice about? Okay. You can just put that they reflect across it. All right, going to the next. This one shouldn't take too long. Is that mapping? Is that a one-to-one? No. So will its inverse be a function? No. Not a one-to-one, inverse not a function. Is a one-to-one, inverse is a function. All right, very last part of this. It's kind of finishing up this whole inverse idea. So, we talked about the mapping. You switch the x and y's. We talked about what it looks like on the graph. It reflects across the y equals x line. Now, whenever you're looking at an equation, I give you an original equation. I say, okay, give me the inverse, the equation to its inverse. This is how you would do that. Okay, that's those 4 little steps over there. First thing I'm going to do is I'm going to put y in for f of x. It's going to make my arithmetic a little bit easier, having y in there instead of f of x. The very next step, I'm going to switch x and y. So literally, where it's written, where y was, I'm going to write x. Where x was, I'm going to write y. After that, I'm going to solve for y. Now, before we get into that, even though I'm sure you were all doing algebra problems over summer in your free time, let's make sure we're clear on what those steps need to be whenever you're solving. Raise your hand if you've ever heard of PEMDAS. Okay, whenever you're solving for a variable, you are going to do the opposite of that. SADMAP. So the S and the A, those two stand for what? Do what?
Subtraction and addition.
Subtraction and addition. I would kind of take them two at a time here. Is there anything and getting y by itself? That's what solving for y means. Is there anything over here that is being added or subtracted that I need to move first? The 4. The 4 is being added. So to move plus 4, I would do what? I would subtract 4 from both sides. So I now have x minus 4 equals 2y. I've done my subtract and my add. Now I'm on divide and multiply. Is there anything that is dividing or multiplying by that I need to get rid of? It's being multiplied by 2, so to get rid of that I need to divide by 2. Those cancel. So now I can say that the inverse, so that's that little, looks like an exponent of -1. The inverse of f of x is x minus 4 over 2. Now, I do want to point this out, and this is just across this whole class, across this whole year. If you do a problem and you get an answer that looks different than somebody else, it does not necessarily mean that you did it wrong. Okay, if some person got what I have written up there, the person next to them had this, and then the third person at that table had this. Guys, those are all the exact same thing. Okay? So make sure that just because it looks a little different, it does not necessarily mean you did it wrong. So last thing is you're just going through another example of that down there. After you're done with that, if you are 100% sure that you did it correct, awesome. After you're done, if you want to check to make sure that you did do it correct, here's the key to the notes right here.